So, lest you think calculus is not useful, I know you all do, I gave you a motivating example. So I gave you an example that will save your life. Okay? So this is the kind of problem we want to be able to answer. So if you look at example 1. So a careless scientist dropped a vial and has exposed the world to a deadly airborne virus. Let's say a zombie virus. Okay, for fun, we don't like zombies. The outbreak of the virus spreads in roughly a circular pattern. You see on the news that the outbreak has currently spread over 4 pi square mile circular region, and your house is right on the edge of the infected region. Preliminary findings show that the area of the outbreak is spreading at a rate of 10 pi square miles per hour. You immediately jump in your car, which doesn't start, of course. You're going to have to escape on foot. How fast do you have to run to outrun the infection? So, well, and eventually it'll be quarantined. You just have to outrun it for a bit, I guess. Come on, don't you have any massive viral outbreak experiences? So we can't answer this yet, but we will be able to. The idea behind related rates is that you can take an equation. Let me give you a simple equation. You can take an equation like the Pythagorean theorem. X squared plus y squared equals z squared. Right? This is the Pythagorean theorem for if you have a right triangle with legs x and y, and then hypotenuse z. The idea is we're going to treat each of these lengths as functions of time. Okay? So depending on the situation, these side lengths of this triangle may be growing or shrinking with time. So if you assume that these lengths are growing or shrinking with time, then what you can do is derive both sides of this equation with respect to time. So assuming these are functions of time, I can take d dt of both sides. And that will give me a relationship between the rates at which everything is growing or shrinking here, which is why it's called related rates. So how do you think we would do this? Now remember, time is not the same variable as x. Right? X is a distance over here. So how would I take the derivative of x squared with respect to time? Well, so first you would have to take care of the square, right? You do the derivative, you have an outside and an inside again. This is almost exactly the same as implicit differentiation. Outside, inside. So you do the derivative of x squared, which is 2x, times dx dt. The derivative of the inside, the derivative of x with respect to t, dx dt. Plus, then you move on to y squared, which is going to be more the same, right? This is the outside. This is the inside. So the chain rule says bring the 2 down. So 2y times dy dt, because y and t are different variables, so you don't know what that derivative is. And then finally, on the other side, you'll get 2z dz dt. So if we know, for example, the way related rates works is the problem is going to be set up so you end up knowing all of these quantities except one. Right? If I somehow give you all of these quantities except dz dt, then you can figure the rate at which this length is growing or shrinking. Okay, so you have to have an association in your head. dx dt, dy dt, and dz dt are all rates. And they're going to tell you how fast something is growing or shrinking. And you can tell in a problem that something is a rate because it'll have like per second. Right? It'll say like, this side is growing at 2 inches per second. Then you know it's a rate. Or if it has per minute or per hour. Something per rate of time you know is going to be one of these rates. So we're going to see how we can use this technique of deriving both sides with respect to time in order to solve some fairly complicated problems. Let me give you some simple examples. So let me do example 2 here. It says if 2x plus 3y equals 12, so this is my relationship between x and y, and x and y are differentiable functions of t, with dy dt equaling -2, I want you to calculate dx dt. So whatever x and y are, there's no situation to go with this. I just have an equation, and I know that the derivative of y with respect to time is -2. And I need to find the derivative of x with respect to time. What do you think I can do?
Differentiate, plug in.
Derive the equation. Take d dt of both sides. Right? Because I'm trying to find dx dt, and I have dy dt, I know I want to do the derivative with respect to t on both sides. So I'll come over here and do that. T. So what happens here? Derivative of 2x with respect to time. So the derivative of x is just 2 normally, but because it's with respect to time, what do you have to put? dx dt. Plus, normally this would be 3, but with respect to time, dy dt, which we're going to plug in for, absolutely, equals 0. Right, so when you take the derivative of both sides, this is what you get. But we know this guy. And we don't know this guy, that's what we're trying to find. So if we plug in what we know, 2 times dx dt plus 3 times -2 equals 0. 2 times dx dt minus 6 equals 0. You can add the 6 over and divide by the 2. Dx dt is 3. So this is the mechanics. This is how the actual calculus and algebra will work once you get your problem set up. So 3 is similar, but slightly more complicated because I give you a more complicated equation. I'm giving you x squared plus y squared equals 29. Y and x are both differentiable functions of time. And then I give you 2 quantities. I say dx dt equals -6 when x equals 5. And I want to know what dy dt. What do you think?
Solve for y first.
Okay. Do I need to solve for y first?
You're going to have a y, so you're going to have to do it eventually.
So you're going to have to do it eventually. Yes, I agree. I agree. But maybe I don't see that there's going to be a y left. Because in the other one, there wasn't a y left. So maybe I'm short-sighted and I don't see that there's a y left. Since I'm trying to get dy dt, I'm going to have to take the derivative at some point in time. Okay, so I'll take the derivative right now with respect to time. That's how we're going to get to a dy dt. Take the derivative with respect to time. Derivative of x squared is 2x times, check. Derivative of y squared, derivative of a constant, So in this case, because the y was squared, you're absolutely right. We still have a y left in our equation. So if you look at what I'm given, dx, dt, and x, dx, dt, and x, I'm trying to find dy, dt. I still have one variable not accounted for. I still don't know what y is. So how do I figure out what y is? Plug in 5 for x, where? In the original equation. Right, this original equation relates x to y, and I'm only concerned about what happens when x equals 5. So because I need this extra variable y, when x is 5, I'll solve for it over here. So by plugging in x equals 5, 5 squared plus y squared equals 29. 25 plus y squared equals 29. Y squared equals 4. Y equals plus or minus 2. So we're actually going to end up with 2 different answers. There's 2 possible y values. So in here, when y equals, so when x equals 5, then dx dt equals negative 6. And let's do y equals positive 2 first. Then we plug everything in. 2 times 5 times negative 6 plus 2 times 2 dy dt equals 0. So it's like 60 negative plus 4 dy dt equals 0. So it looks like 60 over 4. So for this one, it's positive. For the next one, when you do y equals negative 2, then we would have to have 2, 5, all the same, except we plug in negative 2. So everything simplifies the same. You end up getting negative 60 minus 4 dy dt, 0. Dy dt equals, this time will be negative. Do you know why you're getting 2 answers here? So think about, do you know what this equation looks like in the xy plane? It's a circle, right? Circle of radius root 29, but when x equals 5, you're over here and down here at 2 different y values. So then, in one case, you're going to, if dx dt is negative 6, then x is going this direction, and it's asking how fast y has to change to keep up. So it's asking the slope of this line. But if you're down here, x is going negative and y is going, how fast does y have to change to keep up? That's not usually the case, but if you don't proofread well, that's what happens. Okay. So the point here is, the main point I wanted to show you is sometimes if you're missing one of the pieces of information, you can go back to the original equation and solve. Right, over here, when we first did our derivative, we were missing y, so we went back to our original equation and solved. Another point, or another question I want to ask you, why don't I just plug in from the very beginning 5 for x? Because I eventually do, right? I want to know what happens when x equals 5.
And took the derivative to 0.
Yeah, so that's assuming that x is always constant. When you plug in 5 for x, it's saying no matter what y is, x is 5. But that's not the case. X is actually changing, right, as y changes. So that's oversimplifying the situation. X is not always 5. It's just at that.
When x equals 5.
When x equals 5, we want to know what happens, but we cannot plug in that x equals 5 until the very end, after we've done all the calculus. Okay, let's try one. Words, I guess. More words. So for a particle is traveling along a path given by the graph of y equals cos pi x. So you kind of have a picture of what's happening. I like pictures. You have y equals cos pi x. Guess what's the period of cos pi x, by the way? Well, the period of cos x is 2 pi. What's the period of cos pi x? 2. Right? The period is the formula for your period, if you remember. The period equals 2 pi over whatever's in front of x. So this guy starts repeating at 2, which means his mean here is at 1. This is at about half. This is at 3 halves. So there's a particle traveling along this path. I guess he's having a good old time. And then I want to know when x is 1/2, how fast is the y coordinate changing? So I tell you, I'll give you a little piece of information. I say when x is 1/2, I know that the rate, the x coordinate is increasing. If you read it right there, the x coordinate of the particle is increasing at a rate of 2 inches per second. So at this point, I know that my x coordinate of this particle is increasing at 2 inches per second. And I want to know how fast is the y coordinate increase. So let me label what I know in terms of math, okay? So I know that dx dt is equal to what? 2. The rate at which x is increasing, right? Dx dt is a rate. The rate at which x is increasing is 2 inches per second. Dy dt, I don't know. And I know dx dt when x equals 1/2. So this is my diagram, just to help me wrap my brain around it. This is my information written in terms of math. Now I have to actually go to my equation and do some calculus. So if y equals cos pi x, and I'm trying to find dy dt, I need to hit both sides with the derivative. On the left side, it's just dy dt. There's nothing tricky. What happens on the right? Derivative of cosine is negative sine. Keep the inside the same, right? It's a chain rule. Outside is cosine, inside is pi x. So negative sine pi x times what? Derivative of the inside. Dx dt is definitely going to be in there. What else do I need? Pi, right? This is inside, this is outside. Derivative of the outside, negative sine. Derivative of the inside, well, usually the x just goes away and leaves you with pi. But since I'm deriving with respect to t, I also get dx dt. So this is inside of my sine function, and this is being multiplied out. Got my information down, took my equation, derived it. Now I need to plug in everything I know to solve for what I'm missing. Right? This is what I'm missing. I know x, and I know dx dt. So I should be able to figure this all out. dy dt equals negative sine pi. I'm going to plug in 1/2 times pi times 2. So dy dt equal to, I have to calculate sine of pi over 2. What's that? Right, 1. Well, negative because of the negative out front. Sine of pi over 2 itself is just 1, and then you keep the negative out front, times pi times 2. Negative 2 pi. Yeah, and because we were given units here, because x is moving in inches per second, y is also going to be moving in inches per second. So that would be your rate, dy dt. So are you going faster in the x direction or in the y direction? At x equals 1/2.
What?
In the y direction, right? Because this is 6.28, negative 6.28. Why is it negative? Does that surprise you? It's going down, right? Look at the curve. As x goes in the positive direction, y is going down. So okay. Cool. So let's fill our balloon.
You said the derivative of pi is pi.
No, I never said that. Did I say that? I take that back.
Zero, right?
The derivative of pi is 0. The derivative of pi x is pi. Because of the x in here. That's where this is coming from. Because of the x in here, that's where this is coming from. But if it were just pi, yeah, the derivative of pi is 0. Okay, so number 5, you're filling a balloon with water. When the radius of the balloon is 1 inch, the radius is changing at a rate of 1/5 inches per second. How fast is the volume of the balloon changing at that time? Okay, so we have a balloon. So even though I suppose a balloon will not be perfectly spherical, we will assume that it's perfectly spherical to make our life a little easier. When the radius is 1 inch, the radius is changing at 1/5 inches per second. Here's my picture. I'm filling water, putting water in here. Ooh. Perfect. Put water in here so you can really visualize it. Perfect. Now, when the radius of the balloon is 1 inch, then the radius is changing at a rate of 1/5 inches per second. So what am I going to use to talk about the change of the radius? dr dt. Now, the problem with this, so here's the radius. But the problem with this is I didn't give you an equation. Right? So this is where it starts getting tricky. Right? You have to come up with the equation that you need to answer the question. And the question it asks about is how fast is the volume of the balloon changing? So in order to come up with how fast the volume of the balloon is changing, which is going to be, I'm going to call dV/dt, I need a formula for volume of this sphere.
Do not remember.
Oh, oh, I bet you they have it somewhere in the front or back of the book. I can give it to you.
Do not remember.
R squared.
R squared is area.
Pi r cubed.
So it's like
Okay, it's got a pi and an r cubed.
4/3.
4/3. Yes.
Pi r cubed or something.
4/3 pi r cubed. That is correct. That's the volume of a sphere. So you have to somewhere come up with this, somehow, somewhere, I don't know, come up with this formula in order to be able to solve this problem. Right? In order to figure out how fast volume is changing with respect to time, you need a formula for volume. So once you have it, and if it comes up on a test and you don't know the formula, you can say, Josh, I don't know the formula for volume of the sphere, and maybe I'll give it to you, maybe I won't. It kind of depends on the formula you don't know. Volume of the sphere, maybe I'll give to you area of a rectangle. I'm going to say, well, it's about time I hold you responsible for area of a rectangle. So, but you can ask. So now what am I going to have to do with this to get at dV/dt? Differentiate. Derive both sides with respect to time. So I come over here, I say, okay, well I know V is 4/3 pi r cubed. I want to get at dV/dt, so I do ddt. The derivative of volume with respect to time is what I'm looking for. Right? That's dV/dt. What happens on this side? 0. Oh, no, it's multiplication. It's multiplication. So when you have a constant multiple, you ignore it. It just comes down. And then you do the derivative of r cubed, which is what? 3r squared times the inside, which is the derivative of the inside, is dr/dt. Right, we're driving everything with respect to time. So you're always going to get these dr/dt's, dv/dt's popping out. So I'm looking for dv/dt when r is equal to 1 and when dr/dt is equal to 1/5. So if I plug in, I'll be able to solve, I'll be able to figure out exactly what dV/dt. 4/3 pi times 3 times 1 squared, because I'm interested when r is 1, times 1/5. 3 is fight to the death. Laser fight. All right.
Square is
1 squared is 1, so we just have 4 pi over 5. What are the units, by the way?
1.
Inches per second? Technically, we have inches, inches, inches per second. So we have inches cubed per second. Volume, right? Inches cubed per second. What do you think?
Great.
So the tricky part here, I think, was remembering, first of all, figuring out that you're working with a sphere. Right? I don't know what you think balloons look like, but you have to assume that a balloon is a sphere here to do anything. Certainly not a cone or a cube.
Or some sort of water top.
Yeah, some sort of triangular prism or whatever they're called. So you assume it's a sphere, and then you need to know the volume of the sphere. Right? The rest is just like the problems we were doing before. You have a formula, you derive it, plug in your nose. Okay. Okay. Example number 6. So a 13-foot ladder is leaning against the house, and the base of the ladder starts to slide away from the house. Now, what's going on here? So the house, my house is black, I guess. Black house. It's all crooked too. Probably not going to stand very long. It's a very poorly constructed house. So, it's too much roof on that. So I have a house, ladders leaning against this guy. Ladders are usually brown, right? And one-dimensional. So I have a ladder leaning against this guy. That's ground. Keep my grass freshly mowed. In case I have to run out of my house and live on the grass. So, ladder leaning against the house. We're dealing with the right triangle here. And it tells me about the ladder. It says it's a 13-foot ladder. So as this ladder slides down the wall of the house, this 13 feet, which is the length of the ladder, is not going to change. Right? The ladder's not going to start growing all of a sudden just because it's sliding down a house. So this doesn't need a variable. And this ladder is 13 feet always. It's constant. If it's a collapsible ladder, oh, that's a good idea. I like that. Absolutely. We're going to put that on our test. Collapsible ladder sliding down a wall.
Does that add a variable?
If I give you a rate at which it's changing, yeah. If I somehow imply that the ladder can get smaller, that would add a z or variable, another variable. So the ladder is, the base of the ladder is sliding this way, and I think I give you information about it. By the time the base of the ladder is 12 feet away from the house, it is moving at 5 feet per second. That's the second unit there. So by the time the base of the ladder is 12 feet away from the house, now this distance is changing. Right, I'll put a 12 here just so we have it marked, but it is changing. I'm going to need a variable for that. By the time this is 12 feet away, this guy is sliding at 5 feet per second. Now, as the ladder slides down, this guy is also changing, and that's what it's asking for. How fast is the ladder sliding down the wall of the house at that instant? So we want to know how fast am I sliding down here. So what I'm going to do is make some variables. I'll call this guy x, this guy y. I could call this guy z, but like I said, he's constant, so I'm not going to bother making a name for him. And what I'm given, what I know I care about dy dt. That's what I'm trying to find. How fast is y changing? How fast is this guy going down? How fast is this distance shrinking? So I'm trying to find dy dt. And what do I have?
X, and you remember examples, it's
Yeah, so I have x, and I have, what's this?
dy,
dx dt. Right, if this side length is x, then this is telling you how x is changing.
and y is
So I know that dx dt is 5 feet per second. X is changing at 5 feet per second when x equals 12. dy dt is what we're trying to find. And then the only other thing I'm going to need, or I might need, we can find it now if you want, is y. I knew somebody wanted to. So when x equals 12, y equals 5. How'd you get that?
Pythagorean triple.
Pythagorean, yeah, you can use Pythagorean again. So this is all my information. This you would have to solve for using the Pythagorean theorem. Because I know forever and always in this problem, x squared plus y squared equals 13. That's my formula. That's what I'm going to have to derive. Squared. X squared plus y squared equals 13 squared. So yeah, x squared plus y squared equals 169. Because I'm trying to get at dy dt, I'm going to derive both sides with respect to t. T. So this will be 2x dx dt, right? The 2 comes down, but then you need to multiply by the derivative of x, plus 2y dy dt equals 0. So then I plug in line up. I know dx dt is 5. I'm going to put a 5 in here. That's when x is 12, so I have to put a 12 in here. I solved for y and got 5. And I solved for this by writing the equation, just so you have it. X squared plus y squared equals 169, but then I plugged in 5 for x, so 25 plus y squared equals 169. Oh no, 12. I plugged in 12 for x. So that's where the 5 came from, because you subtract the 140. So what do we get here? 2 times 12 times 5. 24 times 5, or 10 times 12, 120. Can you multiply these three numbers? Plus 10 dy dt equals 0. So you subtract the 120, divide by 10. Dy dt, negative 12. Yeah, this is a change in distance. This is how fast a length is changing. It'll be feet. It's good that it's negative, right? Since y is going down. Negative is a good thing for us to do. Absolutely. And so, questions so far? Pretty okay? Comes down to setting up the diagram. If you have the diagram and you have the formula, actually the math part isn't too bad. So a bit of our B on this one. So part B is the same situation, but then it asks how fast is the angle between the base of the ladder and the ground changing at that same instant in time. So I have the same kind of setup. My ladder, which is 13 feet, is sliding down the wall of the house. And it's sliding at a rate of 5 feet per second when x is 12. So all this is the same. But the question now doesn't, I don't care about y, I don't care about how fast this guy's going down. I care about how fast the angle between the ladder and the ground is changing. This is how fast is the angle between the base of the ladder and the ground changing at that instant. So if I call this theta, I guess, I don't know how fast theta is changing. So I know all the same information. Right? I know dx dt is equal to 5 when x equals 12. And I also know y has to be 5 when x is 12 because I solved for it. This is my x. So what kind of equation can I set up to help me get at, well, what am I looking for that matter? Right, so I can set up cosine theta, and what am I actually solving for at the end of the day here? How fast is the angle changing? How fast is the angle changing means I need to find theta dt. So I have to get at some kind of function, some kind of equation that has theta in it. Cosine sounds like a good idea. So what would cosine of theta have to equal? Ooh,
Or x over 13.
x over 13. If you did sine theta, you could do y over 13.
I wrote y on mine.
Oh, you put y the horizontal distance?
I was just thinking about like a
Sounds
x,
good.
y plane. Easy.
You derive both sides.
Yeah, so now you gotta do the derivative of both sides with respect to t. Derivative of cosine is negative sine, keep the inside the same, what pops out? d theta dt, right? Because this is the inside function. This is the outside function. So the chain rule says do the derivative of the outside, which is negative sine theta, times the derivative of the inside. The derivative of theta is d theta dt. What about x over 13? Do I have to do a quotient rule?
Nope. 1 over 13.
Think of this as 1 over 13 times x. And then you just derive the x, right? Because it's a constant times x. So it'll be 1 over 13 dx dt, because the derivative of x is dx dt. Okie dokie. Artichoke. I know this. I'm trying to find this. What do I know about this?
Inverse sine.
Oh. Oh. No. What is it? Sine of theta is what? 5 over 13. Right? When x is 12, and we're dealing with this 12, 5, 13 triangle, sine is opposite over hypotenuse. So this guy's actually known. So I'm going to plug in 5 over 13 for sine theta. I'm going to plug in 5 for dx dt. Then this is known, I can solve for this. So my equation becomes negative because there was a negative when I did my derivative. 5 over 13 times d theta dt equals 1 over 13 times 5. So negative 5 over 13 d theta dt equals 5 over 13. So what happens when you divide here? Negative 1. Right, to isolate d theta dt, you divide by negative 5 over 13. Or multiply by the reciprocal. These are the exact same fraction. Theta dt.
What are the units there?
Units,
Radians per second.
the units would be, you can do radians per second or feet per second. Radians is actually a measure of distance. You can actually convert radians to a measure of distance. Do you guys know how to convert radians to a measure of distance?
Probably did at one point.
Here's the unit circle, right? This is radius. Say you want to take your unit circle to have a radius, your circle to have a radius of 1 foot. So then, the arc length formula, S equals r theta.
I did learn this at one point.
So, this arc length here, because r equals 1, s and theta are the same thing. So, whatever, any radian measure, pi over 3 radians is the same thing as pi over 3 feet. So there's an equivalence between radian and a distance measure. It's not usually how you think of it, but you could. So you could label this feet per second or radians per second. Oh my. Oh my. Questions? All right. 2 more. Get out of here. Shadow problem is a classic. Can't get out of here without a shadow problem. Right, you're strolling away from a street lamp at a rate of 4 feet per second. The street lamp is 18 feet tall. How fast is the tip of your shadow moving? And how fast is the length of your shadow moving? So, what's going on? You have a street lamp. Oh, I don't know the yellow part. Maybe that will be under a green lamp. Pretty much looks like a street lamp. I left out a piece of information. You have to know how tall you are in order to do this. So let's write it in there. Let's say you're 6 feet tall. So you're strolling away from a street lamp at a rate of 4 feet per second. You're 6 feet tall. For some of you, that's good. A wish, right? And it says the street lamp is 18 feet tall. So this guy I know is 18. I'm over here. I know I'm 6 feet tall. I know the rate that I'm moving at tells me that I'm moving away at 4 feet per second. And the question is, well, there's 2 questions. The first one says, how fast is the tip of your shadow moving? So what's going to happen is this light is going to hit you and then it's going to get blocked. So that's going to end up casting a shadow right here. So this is your shadow. Oh, I forgot my fork. So there's this one's kind of tricky, but there's 2 different variables. So there's 2 different distances you need to really consider here. Yeah, so one of them is going to be the distance from the lamppost to the tip of the shadow. So this distance, As you get further away, this light is going to hit differently, and the shadow, this distance is going to change. So let's call it, I don't know, x.
Mm-hmm.
Good. And then you can do this distance here, the actual length of the shadow. So I'll do this guy here. Oh, I don't know if I like him. Yeah, I don't like him. Okay. It's too much thinking if you do it that way. Label this one y. The reason I labeled this one y is because what's this?
A constant?
No, the 4 feet per second, what's that?
dy.
dy dt. Okay, so then I have a nice name for this. So I know dx dt, or actually I don't know dx dt, that's what I'm trying to find. How fast is this moving? How fast is the tip of the shadow going? How fast is x increasing? This is what I don't know. I know dy dt is 4. I don't have any information about how far away I am from the light post. And that actually turns out not to matter. But you do have to be pretty clever to figure out your equation here. So what kind of, do you know the relationship you have to use here?
X minus y squared.
So you could try to use the Pythagorean theorem, but the Pythagorean theorem is going to involve this side, which we don't really care about. Okay? But
Can we just put 6 in or something because they get derived away?
so what you need here is the fact that this big triangle, you see the big triangle right here? And the little triangle starting right here are similar triangles. So similar triangles means they're the same exact shape, they just have different side lengths, but the side lengths are ratios of one another. Right? So for example, if I label this guy A, B, C, and I label the blue guy X, Y, Z, right? Where Z is this whole length and Y is this whole length. Then similar triangles tells me that X over A, right, the ratio of X to A should equal the ratio of Y to B, should equal the ratio of C to Z. Yes, so basically this triangle is exactly the same shape, just 3 times smaller. Right? Because it's got, this guy's 6 feet and this guy's 18. One way to tell that you have similar triangles is when you can tell that all the angles are the same. That's one way, it's not the only way. So I know in this case that all the angles are the same because they both have a right, this big triangle and this little triangle are both right triangles. So these angles are the same. And they share this angle. So these 2 angles are the same, these 2 angles are the same, which means these 2 have to be the same. Because 180 minus the other 2 is equal. So what I'm going to do to set this up is use x over a, 18 over 6, is equal to, so here's my equation. 18 over 6 is equal to what? You gotta be. So if we do y over b, that means the whole side length, the whole big side length over the whole short side length. The whole big side length is x.
So y?
Now y, the way I labeled it, is actually this, which isn't part of a right triangle.
X minus
But if you do x minus y, then you get this.
Oh.
So this portion right here is x equals. So my equation is 3 equals x over x minus y. And I need to find dx dt. I would not in any way derive this equation. Okay, because this equation, if you derive it, is going to be a quotient rule, kind of a nightmare. I would simplify this equation by multiplying my denominator up. So in this particular case, I can make my life a lot easier if I multiply top and bottom by x minus y. So 3x minus 3y is equal to x. Or if you subtract the x over, 2x minus 3y is equal to 0. So this is the equation I want to derive, because that's super easy. So I do it. I do it. 3x minus 3y equals 2x minus 3y equals 0. Derivative with respect to time on both sides. So 2x becomes 2 dx dt minus 3 dy dt equals 0. I know dy dt. It's 4. So then I can add the 12 over and divide by 2. So this is 12 added over, 2 dx dt equals 12, divide by 2. Dx dt 6 meters. So the tip of your shadow is moving at 6 feet per second. And you walk at 4 feet per second. So here there were two kind of tricky things. One, you had to know these were similar triangles or else you're screwed. There's really no other way to do that. And then also the other thing I would definitely suggest, if you can simplify the equation a little bit, right, to avoid a quotient rule, definitely do that. So I then said, how fast is the length of your shadow changing? So I asked a different question related to this setup. And so I can do that real quick. Yeah, so one quick way to do that would be to take the length of the shadow is x minus y. So if you want to know how fast that's changing, you'd have to do the derivative with respect to time of x minus y. So this guy is dx dt. The length of the shadow, though, is given by x minus y. So if you want to know how fast the length of the shadow is changing, you can do ddt of it. And that tells you that the length of the shadow is changing at a rate of dx dt minus dy dt. So you know dx dt, you know dy dt. shadow is equal to 6 minus 4. The length at which the shadow is changing. 2 feet or something. So that's not how I did it actually. I relabeled my variables and did it again, but that works better like that. L is equal to x minus y, drive it, and then you get how fast the length of the shadow is changing.
This is a review guide. It's terrible.
Oh yeah. Yeah, I can't wait to make up some review problems for you on this. All right, so let's do number 1. And then we'll call it that. I wouldn't want you guys to leave without knowing how fast you have to run. Because I know over spring break you're going to be running miles to make sure that you're ready for the outbreak. Okay. So the outbreak of a virus spreads in roughly a circular pattern. Kind of starting assumption here. This outbreak is spreading. It's a circle growing. And then it says, you see on the news that the outbreak has currently spread over a 4 pi square mile circular region. So this part, where the outbreak is spread, has an area of 4 pi square miles. So that's what the first part tells me. Then it says, your house is right on the edge of the infected region. So my house is right on the edge here. House. Preliminary findings show that the area of the outbreak is spreading at a rate of 10 pi square miles per hour. So what?
So an alteration.
Virus,
Because it's square miles per hour, I'm going to label this dA. But the area of the infected region is spreading at a rate of 10 pi square miles. So then we jump in our car, doesn't work. You're going to have to escape on foot. How fast do you run from the initial infection site to safely escape the virus? So you're running away from this infection site. So here's the distance to the infection site, and you're running this way. You're like, you know what? I'm going directly away from this. This is ridiculous. So, in terms of, I mean, what would you call this length here? What is this called? What variable would be there? 2. This is R, right?
Mm-hmm.
And what I'm looking for then is dr dt. If I know how fast the radius is growing, then I know how fast I have to run away from it.
Mm-hmm.
So A is equal to 4 pi, dA dt is equal to 10 pi, dr dt I don't know, R I could solve for, right? But what's my equation that's relating all of this stuff? A equals, the area of a circle equals pi r squared. So this is my equation that relates all of these variables, all of these quantities. So if I did want to solve for r, I could do that at the beginning, right? At this instant in time, when the area of the infection is 4 pi square miles, I can solve for r by setting 4 pi equal to pi r squared. So what does r have to equal? 2. Pi's cancel. R squared equals 4. Doesn't make any sense to have a negative radius. So when the area of this circular region is 4 pi, I know my radius has to be 2. And then I have enough information to solve for dRdt. Take your formula, derive both sides with respect to t. This becomes dA dt. The pi is a constant, so constant multiple just follows along, right? Comes down. The derivative of r squared is 2r dr dt, right? Derivative of the inside. And that's what I want to know. I want to know how fast the radius is changing. So dA dt I can plug in. And I know this is here. It's 10 pi. Pi is pi, okay. 2 is 2. R is also 2. So I'm going to put 2 in for R. And then dr dt is what I don't know. So 10 pi equals 4 pi dr dt. Divide both sides. dr dt equals 5 halves.
Mm-hmm.
Like walkways.
It's not too bad, huh? 5 halves, so 2.5 miles an hour. 2.5 miles an hour. So, yeah, that's true. So that's not too bad. You know what? I would probably say this thread is not too dangerous. I might stop and eat some nachos before I go, take my time.